Hi everyone, today we're talking about exponential functions. So what is an exponential function? Well, it is a power function in which the base is a constant and the exponent is a variable. So for example, f of x is equal to 2 to the x is an exponential function. Base is a constant, exponent is a variable. What is very important is all exponential functions have asymptotes and they increase or decrease very, very rapidly. All right, so what are some examples of exponential functions? Here we have f of x equals 3 to the x. You can have f of x equals 1/2 to the x. In either case, the base is a power. You can have e, because e is just a number, to the power of x or to the power of x minus 1. All right. Okay, so how about an example? Well, anything that grows very, very quickly is an example of exponential growth. So for example, if you happen to catch a certain bacteria, it will multiply in your body over a matter of hours. And whereas you had, just a few, you will have millions and billions and trillions over a few hours. So this is an example of exponential growth. Same thing, if you take antibiotics, within a day or two, they're all dead. That's exponential decay. All right, what is important to note up here is that an exponential function has a base b to the power of x, and it could also have another coefficient next to it. All right, so we're going to get to that in a little bit. Okay. Well, what are some properties of exponential functions? First and foremost, this is the graph of an exponential function. This is how it looks, and you can see that it starts to increase very, very rapidly. The domain of exponential functions is always all reals. Always all real numbers. It requires minimum thinking. You just should know that for exponential functions, the domain is always all reals. All right, the range in this case is 0 to positive infinity. And you can see there is a y-intercept at y equals 1. Well, what about the x-intercepts? Well, as it turns out, there is an asymptote at the x-axis. So if the x-axis is an asymptote, the graph comes exceedingly close to but never touches the x-axis. Therefore, there are no x-intercepts. All right, and we can figure out the end behavior. Let's do the positive infinity first. As x approaches positive infinity, so as I go further and further to the right, my graph goes further and further up to positive infinity. But as I move to the left, my graph goes down and approaches a y value of 0. Right? And it's very similar for exponential decay. Everything is the same, except that as you go towards the right, your graph approaches 0. As you go towards the left, you go to positive infinity. Now, when you have the graphs given to you, you can tell exponential growth or exponential decay. So always remember that for growth, as you approach the positive infinity values, your graph approaches a y value of infinity. And for decay, as you approach the positive infinity values, your graph decays to 0. Well, that's if you have the graph. What if you don't have the graph? What if you're looking at an equation? All right. Well, all exponential functions have the form b to the x. Now, we call this exponential growth if b is higher than 1. So for example, 5 to the power of x, 3 to the power of x, and so on. And it's exponential decay if b is between 0 and 1. For example, 1 over 2 to the power of x, that's decay because the number being raised to the exponent is less than 1. It's between 0 and 1. All right, so let's classify the following as growth or decay. In the first case here, the number being raised to the exponent is greater than 1, so it's growth. Here you have 0.5 to the x, this is decay. Here you have 1 over 3 to the x, this is decay. All right, now here we have 1 over 4 to the power of negative x. Don't let that fool you, because if you have a negative exponent, you're supposed to flip this 4 over 1 to the power of positive x, and you can see that this one is growth. All right, well, let's graph our very first function. All right, we're going to graph 2 to the x. So we just said that all exponential functions have asymptotes. The default case when there are no translations is asymptote x equals 0. Y equals 0. All right, so y equals 0, that's the x-axis. All right, well, what about the y-intercept? This is when x equals 0. So 2 to the 0 is equal to 1, meaning the y-intercept is 0, 1. Now, in order to graph, I first identify whether this is growth or decay, and this is growth. All right? To graph a function that is growth, I pick certain x values, and the values that I pick are negative 1, 0, 1, and 2. Right? So negative 1, 0, 1, and 2. I always pick these values because values less than negative 1 will give an answer that is too tiny, and greater than 2 will give answers that are way too big. So let's go ahead and plug these in. 2 to the negative 1 is really 1/2. So that's 1/2. 2 to the 0 was 1, as we just said. 2 to the 1 is 2. And 2 squared is equal to 4. So let's graph these. At negative 1, we're at 1/2. At 0, it's 1. When x equals 1, y is 2. And when x equals 2, y is 4. Okay. I have to label or to show my asymptote. And here's the graph. There you have it. And you need to show that it follows the asymptote on the left side, and that here it increases without end on that side, and that it increases very, very quickly. All right. Well, let's talk about domain. Exponential function, domain is all reals. There is no x value that you could put in the exponent that will give you an undefined value for the y value. So domain is all reals. All right, what about the range? Well, this is going to start at the asymptote, and it resides on the positive side of the coordinate system. So it's all the values starting at 0 going to infinity. Since 0 is an asymptote, it's an parenthesis, open, not closed. All right, so the limit as x approaches negative infinity is 0. Positive infinity is infinity. This function is continuous everywhere on its domain. All right, there are no discontinuities. All right, here we have 3 to the negative x, and we know that 3 to the negative x is decay, right? Well, the asymptote is still the same. It's y equals 0. The y-intercept, it's 3 to the negative 0, which is still 1. So it's at 0, 1. Now, in the case of decay, I choose my points a little differently. I go from negative 2 to positive 1. So let's go ahead and plug these in. Well, 3 to the power of negative 2 is just 3 squared, which is 9. Here we have 3 to the power of positive 1, which is 3. 3 to the 0 is 1. 3 to the 1. 3 to the minus 1 is 1/3. All right, well, let's graph these. At negative 2, we're at 9. Negative 1, we're at 3. 1 1/3. We've got to put the asymptote here. And again, you have to show that on this side it's going to follow the asymptote, and here it's going to increase very, very rapidly. The domain for an exponential function is always all reals. I don't even have to think about that one. The range is still 0 to infinity. This time, as x approaches negative infinity, f of x approaches infinity. And as x approaches infinity, it's 0. There are no discontinuities, so it's continuous everywhere. All right, now, these were just your basic, boring, no transformation default cases. But we got to make things a little bit more interesting, right? All right, well, the same techniques of transformations also apply to exponential functions. Remember that a vertical transformation will also shift the asymptote along with the graph. So if the graph moves up 2 units, so does the asymptote. All right? Well, here are a few different transformations applied to 2 to the x. All right, well, here we have 2 to the x, and we have 2 to the x plus 1. All right? Here, since the plus 1 is applied to the x, this is a horizontal translation. And if it's 2 to the power of x plus 1, if we set that to 0, it's translated towards the left side. So here, there is a translation to the left. All right, what about here? We have 2 to the power of negative x, right? This is a reflection around the y-axis. Well, what do we have here? I have a factor of negative 3 applied to the 2x. Well, what does the negative do? The negative will give it a reflection around the x-axis. Well, what does the 3 do? The 3 is a vertical dilation, so it'll increase towards the bottom even more quickly. Okay, so it's like you've got a string and you're pulling on it, so the y values will increase more rapidly. All right, so we talked about constants being our base. Well, what about the favorite constant of everybody who loves math, the natural base, right? Most real-world applications that deal with exponential functions have e as their natural base. Well, what is e? Where does this e come from? Well, it's actually labeled e because the mathematician Euler, yes, it's spelled like this, but it's pronounced Euler. He was the one that came up with this, so it's named after him, e. Okay. So this is called the natural base. Well, where does it come from? Well, as it turns out, this factor here, 1 plus 1 over x, is something that shows up all the time. And you'll see more and more of it as you do Calc AB, or more importantly, Calc BC. And it's very often what we have to do to 1 plus 1 over x is raise it to the power of x. Well, okay, fine. And even more often, what we have to do to it is see what happens to this function as x approaches infinity. So you could imagine, oh my gosh, I'm raising this to the power of x, and if x is infinity, then oh my goodness, this is a huge number. Well, you forget that you're already dividing by x, right? If you were to plug this into your calculator, 1 plus 1 over x to the power of x, and graph it, you will be surprised to learn that this approaches a certain value and it levels off. It levels off at a certain value. Well, guess what that value is? Yup, it's 2.71828818, and so on and so forth. Well, that is called E. That's where e comes from, right? So it's just the limit of that factor as x approaches infinity. All right, so if when that ever comes up on Jeopardy, you can thank me. I want live on-air credit, okay? All right, well, let's graph e to the x then. All right, well, let's e to the x. Whether you have 2 to the x, 3 to the x, or 2.7 to the x, your asymptote is still going to be the same. Y equals 0. The y-intercept, well, this time it's e to the 0. It's still 1, so it's 0 to 1. Now, is this growth or decay? Well, it's growth because it's 2.7 to the power of x, right? So I choose my points accordingly. Now, we're going to plug these in, and of course, we're going to use our calculator to figure out these values here, right? So we're going to have e to the minus 1, e to the 0, we know is equal to 1. E to the 1 is 2.7. We don't have to be too exact graphing it. And then we have e squared. You'll come to learn throughout this chapter that e squared is 7.4. So here we have 1, 2.7, 7.4. And e to the minus 1 is actually 0.37. Okay? So let's try to graph this one. When x is minus 1, we're at 0.37. Here we're at 1. At x equals 1, we're at 2.7. And then at x equals 2, it's 4.7. My asymptote is still the same. Hasn't changed. And look at that, everybody. That's e to the x. Same domain. Same range. As x approaches negative infinity, we're approaching 0. And on the other side, we're approaching positive infinity. And we love exponential functions because they are continuous everywhere. All right, here's a much better one now. So where is the asymptote for this one? Well, this has a shift upwards of 3. So the asymptote is going to be y equals 3. Well, what's the y-intercept now? Well, it's e to the 0 plus 3, whereas before, our y-intercept was always at 1, right? It was always at 1. Now we just move 3 up, so it's at 4, okay? And we know that that's the same here. Okay, so what do we have here? We have e to the minus 2 plus 3. Here we have e squared plus 3. And here we have e to the 4 plus 3. Now, e squared, we said was 4.7 plus 3 is 7.7. Now, I know that e to the 4 plus 3 is going to be a number that is way too big for me to graph here. And that just leaves me with e to the minus 2 plus 3. And e to the minus 2 plus 3 is 3.1. All right, so when x is minus 1, we're at 3.1. Right about there. Here we're at 4. Here we're at 7.7. My asymptote is at 3. And there. All right, so same domain. Range is now 3 to infinity. As x approaches negative infinity, we approach the asymptote value. And here we're at infinity. All right. Well, let's apply this. So one application of this is the compound interest formula, and I know you've seen this in Algebra 2. Well, this is when you have some money invested in a account that gives compound interest, compounded n times a year. So for example, if interest is compounded quarterly, then that's 4 times a year. So n is 4. N is the number of times the bank pays you interest. If it's semi-annually, then the bank is paying you interest twice a year, so n is equal to 2. Well, here is the formula. P is the principal, That's how much money you have in your pocket when you go to deposit the money. R is the rate. Of course, it's always in decimals. N is the number of times a year that you are paid interest. And T is time in years. All right. Well, let's see. Well, here we've got this Mrs. Salzman, lovely lady, who invests $2,000 into an educational account for her daughter when she is an infant. The account has a 5% interest rate. If she does not make any other deposits or withdrawals, what will be the account balance after 18 years if interest is compounded quarterly or daily? So there was an A and a B part for this. Okay, let's write down our preliminary information. Principal is $2,000. The interest rate R is 5%, which is 0.05, and our T time is 18 years. All right, so for part A, interest is compounded quarterly, so N is equal to 4 because it's 4 times a year. So A is equal to P 1 plus R over N to the power of NT, 2,000, 1 plus 0.05 to the power of 4 times 18. All right, and what we're going to do is we're going to plug this in our calculator. If you can do it mentally, boy, that's awesome. I sure can't. All right, so we have 2,000, 1 plus 0.05 over 4 to the power of 4 times 18, and we have $4,891 and 84 cents. So it's important here to go to the hundreds place and to round properly because you do not want the bank to make any errors, right? Even if it's a penny, you can't be off. All right. Well, here N is daily. I'm sorry, it's compounded daily. So N is 365. So they're paying you interest every single day of the year. Man, we are going to make a lot of money with this option, right? Well, let's see. So this is going to be 2,000, 1 plus 0.05 to the power of 365 over 4 times, 365 times 18. All right, so I do second, enter to get my equation back. I'm going to change the 4 to 365. So here's a 3. Now I do second, insert, 65. And the 4 again, here's a 3. Second, insert, 65 times 18. Boy, it's going to be so much more money. Ooh, yay. So much more money, right? Why is that? Now we have 4,918.90. So what was the balance? What was the difference? Here we're at 4,891, and this is 4,918. It's not that much. It's just a few dollars. Well, why is it that when that number goes from 4 to 365, there isn't that much difference? Well, it's because up here we said when you have 1 plus 1 over x to the power of x, and this goes to infinity, remember? It all levels off. It's not gonna increase with that bound. We have the same sort of situation here. Look, 1 plus something over something to the power of the denominator. Well, it's not gonna increase with that bound when n increases to infinity. Isn't that fantastic? Isn't that cool? That really, really is. So we can take that then Now this is just a constant. If I could ignore that for a minute, then I have 1 plus 1 over n to the power of n, right? Just what I had before. And if that goes to infinity, what is all that gonna go into? Well, that's gonna turn into e. Okay, so now suppose you find a bank account that pays you not daily, but continuously. Every second, every millisecond of every single day, they're paying you interest. So now you're like, oh my God, I'm gonna really make a lot of money. But what happens? This factor turns into e as n approaches infinity. So my formula turns into a equals p e to the rt. And I call this the Purdy formula because it's, well, Purdy. It's aka, otherwise known as APERT. Well, here it is. This formula is used only when interest is compounded continuously. So in this case, she's lucky. She's shopping around. And she has an account that will pay 5% interest just like before, but now it's compounded continuously. Well, now how much will it be after 18 years? Well, let's see. If A is equal to P e to the RT, then this is 2,000 e to the 0.05 times 18, and let's see how much money that is. 2,000 e to the power of 0.05 times 18, $4,919 and how many cents? 21 cents. So $4,919.21. Oh my goodness, so much more money than that, right? Well, that's because E levels off. Okay. In addition to investments, populations of people, animals, bacteria, and amounts of radioactive decay can also change at an exponential rate. Here are a few models. So we have one formula here. All right, so we have one formula here, n equals n naught, 1 plus r to the t. Okay, so what is n naught? This symbol, where you have a subscript of 0, is called naught. So n naught, that's called the initial, right? So you're used to, for example, initial velocity being vi. I can also say v naught, all right? That means initial. So n equals n naught, 1 plus r to the t. This n is the final amount, whereas n naught is the initial amount. This formula is used when something is growing at a constant rate. So for example, you know that the population is growing at 4% every single year, all right? We have another one here, if something is growing or decaying continuously, like for example, radioactive decay, every second of every day, this is decaying. So we use this one. All right. And one thing, sorry guys, that was my 3-year-old. He has a complaint about his older brothers. I'm sure you understand. Okay. So when we're talking about growth, we usually take a positive value for r. So we'll say, okay, r is positive 0.05. And when we're talking about decay, we'll use the negative value. Okay. Well, a state's population is declining at a rate of 2.6% annually. The state currently has a population of approximately 11 million people. If the population continues to decline at this rate, predict the population in 15 years. Okay, well, n naught, the current population, is 11 million. Now, I don't know about you, but I don't like to sit there and keep writing 6 zeros all the time. So I just say 11 million. In my numbers and in my calculations, I'm just going to put in 11. But then I need to keep in mind that my final answer represents millions and so on and so forth. All right, the rate is 2.6% and it's decreasing, so it's negative 0.026. T is 15 years. All right, so n is equal to n naught, 1 plus r to the t. So this is 11, 1 minus 0.026 to the power of, to the power of 15. All right, so it's important to put this one as well. 11 times 0.974 to the power of 15. When you're asked for a model, we usually do the subtraction or addition here, and we write that to the power of x. And finally, 11 times 0.974 to the power of 15 is 7.409. Okay, what does that mean? Does that mean that after 15 years there are 7.4 people left in the state? I don't think so. Remember, this was all in millions. So n is, you can either say 7.4 million, okay, and this is approximately 7.4 million because we're doing quite a bit of rounding, right? You could also say 7,409,000 people, right? It's still quite a bit of rounding, so it's an approximation, because if you look at the actual number, it's 7,409,298,000, 7,409,298 people, right? And here you're just totally discounting those 298 people. So this is an approximation, and it's people. All right. Thanks for watching. I'll see you guys in class.